Welcome to our review on reversible reactions. So what we find is that some chemical reactions that take place are reversible, and we've already mentioned one previously of the Haber process. Now what we mean by reversible is that it can go both ways. So if we consider Haber process, then the forward reaction is where nitrogen and hydrogen react to make ammonia, and the backward reaction is where ammonia is broken down to make nitrogen and hydrogen. This diagram then shows us what happens in the Haber process. So what we've got in the bottom left of the diagram there, we've got our gases coming in. So we've got nitrogen and we've got hydrogen. So they're brought in and then put under pressure first of all, and this is a pressure of about 200 atmospheres. They're then going to be pumped into the main reaction vessel. Now that reaction vessel is at a very high temperature of 450 degrees centigrade, and as you can see, those little lines in there are beds of iron catalyst, and the catalyst speeds up this reaction. So as the nitrogen and hydrogen pass through the reaction vessel over the iron catalyst through the temperature of 450 degrees centigrade at the high pressure, then we will see them combining to make ammonia. As it then comes out of the bottom of our reaction vessel there, it's pumped around some coolant. Okay, so we're using water to cool it down, and that means that the ammonia will condense to a liquid. So the ammonia then collects at the bottom where we can just pump it off as a liquid, and any of the unreacted nitrogen and hydrogen head back through the system and into the reaction vessel once more to minimise the waste. One phrase we need to be aware of here is the phrase yield. Now whenever we're talking about the yield, we're talking about the amount of product we make. Now one of the questions they could ask you, all to do with the Haber process then, is to look at a graph like the one on the right there and pick out patterns. So what we've got on the bottom, we've got the pressure. Up the y-axis, we've actually got the yield of our ammonia as a percentage, and then we've got a variety of different curves plotted on there, and those are all the different temperatures. So if you're good at reading graphs, then obviously you can just read the graph and say what you see. However, if you're not the kind of person that likes reading graphs and you really look at that and think, I have no clue what that's on about at all, do the easy way, just learn the patterns. So there are two patterns you need to remember. The first one is that as we increase the temperature, we decrease the yield. And the second one is that as we increase the pressure, we increase the yield. If we think back to the conditions that we've said we use for the Haber process, then we've said we use a temperature of 450 degrees centigrade and a pressure of 200 atmospheres. Now obviously if we look at the graph, we can see that's not the best conditions. Ideally we want it to be 350 degrees centigrade and a pressure of about 450 atmospheres if we were to want the maximum yield there. But the reason we don't do that is because we have to go down the route of a compromise. So what we find is to generate very high pressures would be costly, so we don't go to the maximum. What we've done here by picking 450 degrees centigrade and 200 atmospheres is get a relatively high yield quickly. The conditions that we've chosen will give the lowest cost. So 200 atmospheres of pressure is used because the higher the pressure, the higher the yield. But if the pressure gets too high, we'd have to then invest more into a much more structurally sound plant. As soon as you get up to very high pressures, we need very specialist machinery in order to withstand them. And the more specialised your machinery gets, the more expensive it gets. So 200 atmospheres is a compromise. It increases the pressure to increase the yield, but not to the point where the machinery gets too expensive. We are going to increase the rate of our reaction by using a catalyst, and we're also going to increase the rate of our reaction by increasing the temperature. So we know from our graph that the higher the temperature, the lower the percentage yield, but we need a high temperature to get a reaction rate that's fast enough to make it worthwhile. So that's why we pick that 450 degrees centigrade, because it's not going to have too much of a detrimental effect on the yield, but it is going to mean the rate of reaction happens faster. And remember that one way that we can also reduce the cost is by reacting our unreacted gases. So basically we're going to recycle them. Anything that's not actually used to make ammonia gets pumped back into the system so that then it has another chance, if you like, to react.